So let's get started on our field trip, everyone. Welcome to the first session of our 2021 MagLab virtual open house. Today, we're going to take a field trip with one of our esteemed educators, Carlos Villa, who's going to tell us a little bit about, why are magnets special? And, what does it look like when, you actually come into the National High Magnetic Field Laboratory, the largest and highest powered lab here in the United States, the only magnet lab here in the United States, the largest and highest powered lab in the world. Whew, tongue-tied already, Carlos. It's going to be a whopper of 2 weeks of open house events, huh? So let's get started. Carlos, take us away. And I just want to say before I hand it off to Carlos, I hope that everyone who's joining us today has looked at the massive list of awesome free open house events that are available throughout the next couple of weeks. We have just all sorts of fun stuff for you guys to do on Zoom, on our website. There's games, a scavenger hunt launched today. So top couple of finishers that finish first and get the most right answers, we've got some prizes for you. So I hope you're exploring all that virtual open house has to offer. Carlos, take us away. I'm going to mute myself and I'll keep an eye on the questions.
Yeah, feel free to jump in. Any questions, just ask them. I do not mind being interrupted. And the first thing I wanted to do is actually introduce myself, because some of you know me, but a lot of you, I'm assuming, do not. So who am I? My name is Carlos Villa. I am a MagLab educator. I've been at the lab for 19 years. I'm a father of two, Catalina and Daniel, right here next to me today, homeschooling. I'm an alumni of FSU, Florida State University. I am a lover of science, enthusiast of education, and I'm a collector of transformers, and I've got them in my picture here, and I've got a few on my desk too, but I'm also a big Disney fan. If you know Experiment 626, you know who I'm referring to. I'm also a big Marvel fan, so I have to say Wakanda forever, and of course, I am Groot. With that introduction, I want to remind everyone that on Monday, I'll be giving another presentation at 6:30 p.m. talking about the story of attraction. So again, we'll be talking about the science of magnetism a little bit, but also a little bit about how that story unfolded throughout time. So we're going to talk about how magnets were discovered and all the discoveries that went along through that. So that'll be on Monday. And I'm going to plug a few other events that we'll have during Open House. So who are we now? Who's the Magnet Lab? So we're one of 7 magnet labs in the entire world, and I know that some of our MagLab friends are in the audience, so hello to you all. But we're the only magnet lab on this side of the planet, so it's later or earlier for everyone else. And Krista mentioned that we are the highest powered magnet lab in the world, and that's a cool thing. I do like bragging about what we do, and that some of the things that we are able to do is only because these magnets don't exist anywhere else. We have a $58 million budget to operate the Magnet Lab, and that's how much it costs in 2019, but it's free for scientists. We don't charge the scientists. Why not? Because our job is to further scientific knowledge. So if the scientists are going to make discoveries, we want them to come to our lab, do their science, make a discovery, and we want them to have easy access to our magnets. So we don't charge the scientists. It is free. Now, what we do is not all about magnets. The big misconception that everybody has is that everything that we're doing is magnets, 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 magnets. Everything we're doing uses magnets, but it's not all about magnets. We have materials, energy, and life, and those are the holy three that we're always looking at. Those are the big 3 topics that we're researching, and those break down into material science and physics and engineering, chemistry, biology, some biomedical stuff. We've been working on the COVID-19. We have worked on stardust before. We've done geochemistry. We've done a little bit of everything at the lab. I remember my very first year, we actually had a paleontologist coming out, and we had some T-Rex fossils, which was very cool. So we've done a little bit of everything. Now, one other cool thing about the Magnet Lab is that we are actually at 3 different locations. So we've got Florida State University in Tallahassee. We also have a lab at the University of Florida in Gainesville. And then we've got a lab at Los Alamos National Laboratory in New Mexico. All 3 locations together make up the National Magnet Lab. But we do have the 3 different sites, and they all specialize in something a little bit different. I mentioned that the science is free for the scientists. This is where they are coming from. We've got scientists coming from all over the world to our lab. I like to show off this map because the red dot here, this is Los Alamos, where they're snowed in. And you can see all the scientists going to them from the US and from around the world. The blue dot here is the University of Florida, Gainesville, and the purple dot is FSU Tallahassee. So you can see that we've got visitors coming from all over the nation, all over the world, coming to our magnet lab to use our magnets, and that's just cool. One side effect of that is that we get staff from all over the world, and I truly love how international our staff is, because I can say that I've got friends all over the world. I've got friends that are from Russia and China. I've got a friend that just left to go to New Zealand and work at a lab there. I've got friends from Canada. I know we've got friends that are in the audience from Colombia and Brazil. I myself, this is my little dot right here. I was born in Nicaragua, so that's me. And we've got people from all over. I've got friends in Nigeria and South Africa. It's just super cool. And I will say this, during Olympics, it gets a lot of fun, very competitive. World Cup too. I had no idea how soccer crazy we were until we had a watching party and everyone showed up in their jerseys with their horns, and it was a lot of fun. Now, the MagLab is taxpayer funded by the National Science Foundation and the state of Florida, which makes everyone here in the crowd that is paying taxes in the US a stakeholder in our facility. So I want to say on behalf of all of us, thank you for supporting our science. And I want to remind everyone to join us February 27th at 4 p.m. for our virtual escape room. I know nothing about this, but I am excited to participate and try to escape myself. So I have no insider information. I'm looking forward to doing this. It sounds like it's going to be a lot of fun. But right now, Kristen, are there any questions that have come in so far?
So far, we're in good shape. Still just saying hello to everyone joining us. I just want to, since we're recording, this is part of the official presentation. I just want to especially thank all of the classrooms that have joined us today for this virtual field trip. It just makes me feel so warm and fuzzy knowing that there's students watching us from their classrooms, whether at school or at home. We're so happy to have you here. Take it away, Carlos.
All right, if any questions do come up and you've got something you want to know about, by all means, please type it into the chat box and we will ask the question and hopefully get you the right answer, or I'll make up something that sounds right. All right, I can't do that. I've got too many scientists in the crowd, so we'll find the answer. Everyone, I want to introduce you to Nikola Tesla. I'm sure some of you know who he is. If you don't, please look it up. It's an amazing story. I mentioned Tesla because it's a word I'm going to use a lot in the second half of this presentation. I'm going to be talking about Tesla in the way of not the person, but the unit of measurement. So Tesla is actually what we use to measure how strong a magnetic field is. So it's named for the Serbian scientist Nikola Tesla. So just as a quick activity, I want to show you 4 different types of magnets, and I'm going to show you how strong they are so you get a sense of scale of what a Tesla looks like or what a Tesla is. Starting with the fridge magnet. So if you look over here, I know that my kids played with the alphabet magnets forever. I know that I still find lost alphabet magnets throughout our house. And if you measure them, you find out that on average, they're about 0.03 Tesla. So not very strong, but definitely strong enough to hold up a spelling test or some art projects. I'm looking over at my fridge and I'm like, what else do we have on there? We got save the date invitations and all sorts of stuff. But that's about what we need, 0.03 Tesla to hold up those documents on the refrigerator. But we also have our junkyard electromagnets that actually pick up the scrap metal and move it from one place to another. And those come in at about 1 Tesla. And some are going to be stronger and some are going to be weaker. And that's true for all the magnets I'm talking about here. But the junkyard magnets that pick up an entire car at times, those come in at about 1 Tesla in strength. Now the next picture up here is an MRI. And if you've ever had an MRI, that's a very powerful magnet, maybe the strongest magnet you've ever been in. And it's a 3 Tesla magnet. And I know some go down to 1.5, and I know that we've got some that are up to 5 Tesla. So I split the difference. 3 Tesla is going to be about average for an MRI. I believe that most of the diagnostic MRIs that they use in hospitals are about 1.5 to 2 Tesla. But that's where that strength is going to be. Now this last picture here is one of our world record magnets. This is the world's strongest water-cooled magnet. And that magnet that we've got here goes to 41.5 Tesla, but that's not the strongest we have in the lab because we go all the way up to 45.2 Tesla. And we actually have some magnets that we run in Los Alamos that go up to 101 Tesla. Now, the reason I've only listed the 45 is because I'm talking about continuous fields. And the magnets that we have in Los Alamos go to 101 Tesla, but that field lasts for a fraction of a second, as little as 30 milliseconds. So 45 Tesla, we can reach that field, we can hold that field for as long as we need. And that's what we're going with for today. Now, some things about magnets I want you to know. First of all, magnets have poles. All magnets have poles. They all have a north pole and a south pole. And if you cut this magnet in half, the pieces that you broke it into are also going to have north pole and south pole. So it's not something where you can cut off the north or cut off the south. Magnets are always going to have the north and the south poles. And if you take those magnets and you put them close to each other, the north and the south next to each other are going to attract. And the north and the north, or the south and the south, are going to repel away from each other. And that is something that all magnets are going to do. I just want to say as a quick FYI, there are no east and west poles. That's just not a thing.
Hey,
the other
Carl,
thing that, oh, go ahead.
let's just interrupt a little bit because there's a couple of really fun questions that I think actually are working right about now. A question about, are there any stronger magnets than neodymium magnets? So kind of a pertinent question right now while we're talking about those different types of magnets. Go ahead and answer that one.
And neodymium is a neodymium and iron mixed magnet. So it is an alloy and it needs to have the iron in there to work. So what we've discovered is that by mixing iron with a bunch of different types of materials, we can make very strong magnets. Neodymium are among the strongest magnets, and I know that we've got some scientists at our lab that are working on finding other magnets and other chemical mixes that make strong magnets. But as far as I know, neodymium is the strongest commercially available magnets. And that's something I want to say because I do believe I've heard rumors of some stronger materials, but nothing that is available to the public right now.
Excellent, excellent. There was a question, I'm going to reply to it just about how long the MagLab has been in Tallahassee. And I just want to tell everyone, we have proudly been in Tallahassee since October 1994 when the lab was open for science and we actually held our very first open house event. So that's more than 25 years that we've been having some fun in Tallahassee, headquartered at Florida State University. Another question. Oh, there are some questions about water-cooled magnets and whether they're electromagnets or superconducting magnets. I think you're going to get into some of that, so just put that in your mind. And also a question about how we use magnets to power things. So just as you continue into this next section, some things that I know might come up, but just to plant them as seeds. Thanks so much for these great questions. Keep them coming either through the Q&A or the chat feature.
Yeah, the importance of magnets is sometimes lost on some people. They're like, well, I'm not using it and I hear the word stick a lot too, but they say I'm not using my magnets to attract, so why do I need them? I'm like, magnets are all around us. If you're looking, I'm looking around my house right now and I can find 6 or 7 different devices in this room alone that would not work without a magnet in them, including speakers and motors. So magnets are pivotal to the energy world around us because all the generators, except for solar, all the generators are working off of magnets too. So very important that we have magnets. So the other thing that all magnets have is having that magnetic field. And something a lot of people don't know is that the magnetic field does have a direction. And what it's doing is it's actually coming from the north into the south pole. So if you follow the direction of the field, if my arrows want to jump up here, here we go. That field's going from north to south, and that's the direction of the field, and that's important. I often get asked, why do magnets attract and repel? And the answer is because of these fields. Because when you put the north and south next to each other, those fields are moving in the same direction, and so those magnets are going to attract and come together because the fields are lined up. However, if you take 2 fields and put them against each other, south against south, those fields are pushing against each other, and that's when we get motion caused by the magnetic field, because it's going to try and turn that magnet around to attract the other side right here at this point. So the magnetic field is what makes magnets attract and repel. And I'll tell you this, as when my kids were younger, they were watching a show, and on the show, a very famous cartoon character says that they were going to use their magnet to pick something up that fell because magnets stick to metal. And I was like, no, you can't say that. Magnets do not stick to metal. Magnets attract to some metals. And in fact, there are three metals, iron, nickel, and cobalt, that are naturally magnetic. So if you think of all the other types of metals that exist, like gold and silver and aluminum, those aren't going to naturally attract magnets. It needs to be iron or nickel or cobalt. And the magnets that you have at home are made out of iron and nickel and cobalt. Now, I'm going to show you a little trick to remember which are the metals that are naturally magnetic. So watch this. My kids love movies. I love movies. And one of our favorite movies to watch together is this one right here, Monsters, Inc. Now, the thing about Monsters, Inc. is I want you to remember that name, but I want you to remember it slightly different, because at the MagLab, we think about Magnets, Inc. And if you think about Magnets, Inc., ink will always help you remember that iron and nickel and cobalt are the three metals that are naturally magnetic. So everybody think Magnets, Inc., and you're going to remember that iron, nickel, cobalt are your three metals that are naturally magnetic. All right, February 26th, we've got a scientist speed session with our chemist, Lissa Anderson. She's a ton of fun. I like talking with her. So February 26th at 4 p.m. So it'll be after school, so everybody can join us. And I'm going to pause to see if we have any new questions.
We have lots of great questions. A question, are there only three metals that attract?
Only three metals that naturally attract. So there are some metals that if you freeze them, they become magnetic. There are some metals that if you put pressure on them, they become magnetic. And there are some metals that are only magnetic at extremely high fields. So I'm very careful when I say that, because I want to say naturally occurring, naturally magnetic. So the answer is that no, there are more than three that are magnetic. But if I had all the metals here right now in front of me and I put my magnet up to all of them, only those three would attract.
Mm-hmm. Excellent. So let's see, so many questions. They're everywhere. There's so many wonderful questions. I love this. So a question, a little bit more question of like, motors use magnets. Tell us a little bit more about that.
Okay, so here's the thing. Electricity and magnetism are so closely connected to each other that I don't like talking about them separately. We should really be talking about electromagnetism as one force. And that's why we can take electricity and use magnets to make the electricity, and then we can use the electricity to make magnetism. So they're both dependent on each other and they can both cause each other. So it's a very interesting dynamic and something I'm going to talk about in depth more on Monday.
So a question about how do magnets attract? I think you talked a little bit about that, but do you want to just give a little bit more of an explanation there, Carlos?
Yep, you got to have those fields lined up the right direction. See if I can go backwards enough. Here you go. You got to get those fields lined up in the right direction. So when north and south are next to each other and those are opposite poles, those fields are actually going in the same direction to each other. And so they actually come together. And you can see that by the representation of those yellow arrows on those lines. But when it's the same south against south or north against north, they're not going in the same direction. So they're going to push away from each other. So really that's all it comes down to. It's the dependence on the field that creates the attraction and the repulsion.
So a question, can magnets break each other?
Oh, it depends what you say by break. So if you take two magnets and they're very powerful and they attract each other, they can shatter each other. They will absolutely do that. I have lost many expensive neodymium magnets to being too close to a different neodymium magnet. But when they shatter like that, all those pieces are going to still be magnets. So you're not breaking the field, you're just breaking the physical magnet.
Excellent, excellent. There's many questions happening right now about, does the MagLab make our magnets? What are the world's most powerful magnets? Anyone who's asking a question along those lines, we are getting to that section, okay? We are not done. We're just stopping to answer a couple of questions at this stage. We will get there. Here's a spoiler, we design and build our powerful magnets. And Mr. Carlos is gonna talk about, how we do that and what they're made of and how powerful they are. And how we make them. There was a clarifying point, Carlos, about elemental metals. Those are the elements that attract. So yes, that's well said. And I love this question. What would happen if magnets didn't exist?
I don't think life as we know it could exist without magnetism. And I'm going way big picture to the astronomical and space thing, because the sun puts out a lot of radioactive substances, materials. I don't even know what the right word is, but they give out these particles that just aren't safe for us. And Earth's magnetic field actually blocks and pushes away a lot of these materials, making Earth habitable. So if Earth didn't have a magnetic field, losing the biggest field that we have, I don't think life could exist on this planet without the field. So just there alone, no, there would be no people to understand magnets. So that would be the end of that.
How about that for big picture, guys? How about that for how important magnets are?
Yeah.
Mr. Carlos, just because you're talking about the Earth's magnetic field and we're going into this section, you know, I just want to kind of tease what we're going to talk about here and get people excited to talk about the MagLab's magnets, because the MagLab actually houses magnets that are lots and lots and lots more powerful than the Earth's magnetic field, right?
Yeah, we talked about the 45 Tesla being the strongest one we have in Tallahassee, and that's the strongest continuous field magnet in the world. I didn't tell you Earth's magnetic field in Tesla, and I'll tell you right now, I'm afraid I can't write it down to show you, but it's so we're starting with a 0.000045 Tesla. So that is a million times weaker than our magnetic fields that we create at our field. Everybody's like, if it's bigger, it's stronger. Not necessarily so. We actually go smaller to get stronger. So I'm going to jump into the story of magnets, because talking big picture, we got to go backwards, way backwards to 2000 BC to this guy here, who apparently his name was Magnus, and he lived in Magnesia, and he discovered magnets. And I think that's just all too coincidental for me. But that's the story. And we don't know if this is true or not, but this is a story that's been handed down forever, that Magnus was walking his flock, and he noticed that very small rocks were attracting to the bottom of his staff where he had iron nails. And so he took them home and he played with them, and he found out that they would stick to the iron materials in his house. And so Magnus either decided to name them for himself and call them magnets, or he named them for the region of Greece that he lived in, which is Magnesia. There's too many magna in this story for me to find it to be true, but this is a story that's been handed down. Now, what we do know, and this all happened in Greece, of course. What we do know is that William Gilbert was the first person to actually study and write about magnets scientifically, and was the first one to say that, hey, these aren't spirits or ghosts or magic powers or magic rocks. And William Gilbert was actually able to write a book called The Magnet, and talked about how these magnets worked. And he studied them and found out the attraction and the repulsion. And he was the first one to do that. And this happened in England. And then in 1820, Hans Christian Ørsted made a major discovery that started the connection between electricity and magnetism. And what he did was he was setting up in his lab a demonstration that he was going to show off. And a wire carrying electricity fell off the stand and landed on top of a compass. And as he looked over, just as this was happening, he noticed that the compass moved. The needle deflected a little bit and went back to normal. And so he moved the wire and the compass went back to normal, and he put the wire back and it deflected again. And he realized that the electricity was creating magnetism, and that's why the compass was deflecting. So this is a major breakthrough, and it happened 201 years ago. So Hans Christian Ørsted in Denmark made this discovery. And actually, I want to retract that. He's from Denmark. I think he made the discovery in England, actually. But he gave us this major discovery of electricity and magnetism being tied together. So William Sturgeon now took that idea and created the very first electromagnet. And what he did was he created a curved iron rod here. He took some copper wire and wrapped it around the iron rod. And he had a 7-ounce magnet lifting 9 pounds of iron. And that's a major, major breakthrough. And of course, this happened in England. And then in 1827, Joseph Henry looked at that electromagnet and said, you know, if we insulate that copper wire, we can get more turns of wire on that and make an even stronger magnet. And that's exactly what he did. He took the copper wire, he wrapped silk around it so that the bare metal wasn't touching the other bare metal, so that each individual wire was working. And he made the strongest electromagnet up until that point. And this happened in 1827, and Joseph Henry did this in the United States of America. Which brings us to 1994, where the National MagLab was founded in Tallahassee, and we just broke 17's world records. And I'm sure we're gonna break more in the near future, because this is what we do. And I've listed them here. I'm not going to read them off because we have almost all the world records that have to do with strongest types of magnets, and we're working on many more. So we actually enjoy the challenge when one of our records gets broken. We want to earn it back, and that means that we're going to have to push technology and engineering to the next level in order to do that. And we've got some scientists at the lab that are just a little bit competitive, so this is a good push for them too. And of course, we are in the USA too. All right, if you missed the first escape room, we're gonna have a second escape room on March 4th at 7 p.m. Is that a Saturday? No, it's a Friday.
The first one is on a Saturday. The 27th is a Saturday, and then this is like game night at 7 o'clock. It's a Thursday night game night.
Excellent, and this is where I'm gonna stop one more time before I show off all of our amazing magnets to see if there's any questions, and I'm sure there are.
There are a lot of questions. I'm so excited that so many of you have all these questions about magnets. There is a question: what would happen if you put too many magnets together?
I don't think anything would happen other than they get heavier. So the magnets, as you're adding more and more magnets together, they're not getting weaker. Their field is changing size because instead of reaching out into space, their field is working on the magnets around them, but they're not getting weaker. So putting a whole bunch of magnets together doesn't necessarily weaken them or make them go bad.
There's a question about how lines of magnetic flux behave. How do lines of magnetic flux behave? There's also a question about whether we can see the magnetic field. I'm going to answer that one in the chat and send you to an awesome lesson and video that we're getting ready to launch. So you can. There is a way to see a magnetic field. Mr. Carlos has an awesome video about it. So I'll put that in the conversation in the answers. Go ahead, Carlos, take it away with magnetic flux.
Oh my God, flux is such a fantastic word. It's one of my favorite science words. And if you want to know another one, entropy is up there too. Tungsten is a great science word. But flux, so when you're talking about flux, first of all, there is no flux capacitor or flux capacitance. Those are just two things that don't work together. So I'm sorry, Back to the Future fans. It's great fantasy for movies, but it just doesn't work in real life. So when you mention magnetic field flux, what that means is that the field is either changing in strength or direction or location. If I've got a magnet and I leave it on the table and nothing's happening, there is no flux. That is just a magnetic field that is there. But as soon as that field starts to move around other objects, closer, further away, alongside, or the field changes in strength, that's when you've got magnetic flux. And how those lines are behaving depends on how the flux is changing. So it all depends, and there are a lot of variables that go into that, such as the strength and the direction and location. But that's what the flux does. Are we ready to show off magnets now?
I think so. Some of our other questions are in that vein. So let's get to that section and then we'll see what other questions that triggers for all of you.
I want to introduce everyone to our 15 years old now. Is that right? 15-ish years old. This is our 21 Tesla nuclear magnetic resonance, NMR, superconducting magnets. And this is, if you look at that white container inside that picture, oh, I've got my mouse here. There you go. If you look at this white container here, this is what I'm talking about. This is the actual magnet. All of the magnets at the lab that are used for experiments are electromagnets, so they're all dependent on electricity to function. And they all create their magnetic field in a similar fashion by taking electricity and making it travel into coils. But how that works is a little bit different on all the magnets too. So this is a superconducting magnet, which means that the temperature of the wires that are carrying the electricity are cooled down all the way to minus 460 degrees Fahrenheit. If you're familiar with Kelvin, it's at about 1.8 Kelvin, so it's extremely cold, and the only way to make it that cold is with some liquid helium. Now, let's point out some things that are in this room. This is our yellow field warning line. And this yellow field warning line is there to show you where the magnetic field starts around that magnet. So if you cross that yellow line, you're okay. Nothing's going to happen to you. But if you carry your laptop across that yellow line, you are going to lose any information that is magnetically recorded. Credit cards, computer hard drives, those are all going to get wiped out if you go across that yellow line. So be careful there. This black line is where if you cross that line and you're holding anything that is magnetic, iron, nickel, or cobalt, those items are not going to be in your possession much longer because the magnet is starting to attract them. And that's why we've got that plexiglass shield in front of the magnet, so that whatever flies towards the magnet is going to hit the plexiglass and not the magnet. So that's a good thing that we want to protect our magnets. These are the probes, and these are the probes that our scientists put the experiments on. So if you look at the tip here, this is where the experiment actually goes, and it could be any number of different things. I've seen geochemistry samples, rock samples, lava samples, space samples being put in there. I've seen materials, styrofoam, and of course, this is one of the few magnets in the world that can do a high magnetic field and vivo. So we're able to put living animals into the magnetic fields. I have to say this, they go in alive, they come out alive. That's a very important point to say. But we do give them a little sleepy juice so they are asleep while they're in there. Because one of our scientists I was talking with this summer, we asked him, what scares you at work? What's the dangerous aspect of the job? And he's like, well, the rats bite. Okay, not what I was expecting, but there's a story. So these are the probes, and they're big enough to put small animals into, but not big enough for a human to go into. The opening is about 4 inches, so you've got about this much space to go in there. This is the area, the space where the scientists will go downstairs. They'll be underneath the magnet, and that's where they put their probe into the magnetic field. So this is the area where they will enter, put the probe in, lock it in place, then they'll walk out to the back of the room and do their work from the back. What is next? So the top part of this magnet up here, this is where the helium is. So this is the helium refrigerator that fills up and cools the rest of the magnet. And this is where the actual magnet part is. So when the probe goes into it, it's going to be right about here. This is where you want it to be. These are the helium tanks that we have to refill the helium on this magnet to keep it cool. This magnet has been at minus 460 degrees for 15 years. This magnet has not warmed up, it has not stopped functioning, it has been cold all that time. And in order to do that, we got to make sure that we're refilling the helium. Now, we do have a pipe right here. Let me see if I can show you this one. This pipe right here actually takes the gas helium and recycles it. So that gas helium goes back to the other side of the building where we reliquefy it and can put it back to the magnets. On the other side of our building, we have our DC resistive magnets. Now these magnets are not cooled by liquid helium. They are not superconducting magnets. They are resistive magnets, which means as the electricity runs through them, there is resistance. And because there is resistance, these magnets start to heat up as they are working. Now what we have here, let me go back one. As we've got here is a cross section so you can see what's on this magnet. The electricity will go in and out of this magnet, and the water to cool it down will go in and out of this magnet too. So here's the magnet. I've got 2 different DC magnets and they're different sizes. We've got a few of these, I think as much as a dozen DC resistive magnets in the building. And they all look a little bit different, but they've got the same thing. It's a stainless steel container because it's not magnetic. We put the magnet into it and then we connect all the electricity and the water to it. So this is the pipe here. Let me go back one. This pipe here is carrying the electricity in and out of the magnet. And this pipe here is carrying the water in and out of the magnet. So the top one's going in, I believe, the bottom one's carrying it out. And I think it's same for the electricity, though the direction really doesn't matter so much as long as it's going in and out of the magnet. That's what makes it DC. DC stands for direct current, which means that the electricity is going one direction through the magnet. This is what happens when the water is not able to do its job. And what we have here is a magnet that the water did not get to, And so the copper parts of the magnet, which are carrying all the electricity, overheated and actually started to melt. This is not something that happens often, but when it does, we always put it off to the side because we want to show it off during our tours to say, hey, this is what happens when magnets go bad. Most of the time, in fact, nearly all of the time, the computers that are supervising and running the magnets are checking the water and the electrical and making sure that everything is within limits. And if it starts to go out even just a little bit, the computers will shut down the magnet so it doesn't damage itself. But sometimes these magnets go bad and they melt, and that's not a good thing because it takes a lot of plates and a lot of work to replace these. This is our 36 Tesla. So we're getting a lot stronger here now. This is our 36 Tesla series connected hybrid. This is one of our newer magnets. I think it's only about 3 years old. And this one is important, not just for reaching 36 Tesla, but that it uses a lot less electricity to get to 36 Tesla. So that's an important thing too. So I like this magnet. It is fairly new, but there's a sign right here that I always find humorous. And I've mentioned to all the scientists why I love this sign. That sign says access to platform, and this is the platform up here. This is where the scientists will stand when they need to. Access to platform allowed when I less than 10,000 amps, 10,000 I. That means that you're allowed access to that platform as long as the amps that are running through that magnet is less than 10,000. I find that number remarkable, and here's why. A washing machine uses about 12 to 15 amps of electricity, 12 to 15. TVs can use 18 to 20 amps. Vacuum cleaners are using 7, 8, 9 amps. This magnet's running, I think, up to 60,000 amps. And you're allowed to be up on top of the magnet as long as it's less than 10,000 amps. That is a ridiculous amount of electricity going through that. I'm sorry, let me rephrase that word. That is an enormous amount of current going through that magnet. And I just think it's funny that 10,000, you're okay, because that terrifies me sometimes to think about that. Same sign on this side of the lab. So you can see that we have that sign posted many times. I know it's a safety thing, but 10,000 is just an incredible amount of current. This is our 45 Tesla hybrid magnet, and this is the strongest magnet continuous field in the world. And I want to show some cool things about this. First of all, that concrete floor that you're looking at, the last the last four magnets I showed you are all on this side of the building in the DC building. And all of the magnets are on this one solid piece of 3 feet thick steel reinforced concrete. Now, the floor is not something people usually want to look at when they're on tour. I love the floor because it took an enormous amount of cement mixers to come in to Tallahassee, because he came from out of town, to pour this one continuous pour and get all the concrete down to make this happen. This pipe here that you see, and it's not really a pipe, but that's actually supplying the water and the electricity to the center of this. Now, the last two magnets are both hybrid magnets, and the reason that they're called hybrid magnets is because they're actually two different magnets mixed together. So what we have in the very center of it is a DC resistive magnets, and we've got some open house stuff that we're going to show you on how DC resistive magnets work. But they've got a DC resistive magnet that is running electricity and cooled by water. And then we'll take a superconducting magnet and wrap it around that. And the superconducting magnet's got to be cooled by liquid helium, and it's got to be kept cold the entire time. So we've got a water-cooled magnet in the very center, a superconducting outsert around that. And that's why these two magnets are called hybrids, because they're actually not one magnet, but two magnets that are working together to give a combined field in the very center. So this pipe that you see right there is supplying the water and the electricity to the resistive part of the magnet. Let's see what else we've got here. And this is the superconducting part. This is where the liquid helium and the wires for the superconducting part are. And I believe that these are niobium tin superconductors. So not the next generation of superconductors that we're making our new magnets out of, but then again, this magnet is 20 years old now. This red light is going to be flashing, and actually these gates that you see here with the danger written on it, those gates will be closed when the magnet is on. So if the light's not flashing, the field is off and you're allowed to go in there, you're okay. But when the magnet is on, these gates are closed, the light is flashing, and only authorized users and scientists are allowed in that room. I am an authorized person, so I can go back there, not bragging.
And I have exciting news for everyone because in minutes, we'll be releasing a 360-degree video that we took in this area. So all of you will get access to areas that are not accessed by even most of the people who work at the MagLab, including not just the spot that Carlos is showing, but that spot under the magnet and on top of the 45T, which is actually where the scientists work. So you'll all have the opportunity to go, all access behind the scenes to the most special spots of the MagLab in just a few minutes as we get ready to launch all that new content for you for this open house.
That's going to make all of you insiders because I've actually never been under the hybrid. I've been on top of it and I've been next to it, but I've never been under. And there are parts of the lab that I've only been in 1 or 2 years now. I've been at the lab 19 years, so I think I've earned a pass to go everywhere I want, but it doesn't work that way. The bus tunnel is one of my favorite places in the building, and I've only been there twice. And are we showing off the bus tunnel?
I don't think we have 360 of the bus tunnel, but we do have some cool stills.
Yeah, the bus tunnel is an amazing room. Again, the type of electricity and science and engineering that makes you go, wait, you're doing what? So let me show off one of the things that is something very important to this, and that's that blue light. The magnet I told you is the superconducting part of the magnet is cooled by liquid helium. Now, if you breathe in gas helium, you all know that your voice gets very squeaky and funny and everybody laughs, and that's okay. But when you're doing that, you're breathing in helium and you're not getting oxygen. If this magnet were to malfunction, all the helium that is inside of that magnet would be vented outside to prevent the magnet. That blue light would start flashing because it's an oxygen deficient thing. So when the blue light goes off, and I want to say too that everybody that is in this area has an oxygen sensor that they must wear while they're in this area. But when that blue light goes off, that means that the helium is venting out, the oxygen levels are dropping, and then the easy fix is that you step outside and everything's okay for you again. We built in safety systems in this room so that the helium can be vented out very rapidly. But just as a safety thing, when the blue light goes off, you step outside and everything's all right. I want to say real fast that we are excited that we'll be offering our summer camps virtually this year. We're going to have a Camp Tesla, we're going to have our Sci Girls, and we will be doing a Sci Girls coding camp virtually, and we'll be sending coding materials home so the students can be doing the coding at home. And not just doing it online. They'll actually have a system that lets them do the coding and you can test right then and there if your code is working. So that's something that is very exciting that I'm excited to talk about. And we'll get to Q&A and see if there's any additional questions now.
Oh, so many amazing questions coming in. And another question about just what makes the magnet a hybrid. So if you could just spend just another minute going through that idea of resistive magnets and superconducting magnets and how they get to work together, the difference between the two of them. Also cover the temperature of those superconducting magnets one more time, Carlos.
So both of the magnets, both of the hybrids are resistive and superconducting. And I actually was able to ask a scientist over the summer if there's any other types of hybrids that exist. And they said that no, all of them are resistive and hybrid. So there's resistive and superconducting. So there's one type of hybrid that is offered. The superconducting part of it is at minus 460 degrees Fahrenheit, which is about 1.8 Kelvin, which is minus 372 degrees Celsius.
Which is colder than the surface of Pluto.
Yeah, I mean, we're just a few degrees above absolute zero. And when you get to absolute zero, there's nothing, no motion, no energy. It's just nothing. All theoretical, of course. We've never actually gotten there or proved it. But that's another conversation. So we've got two hybrid magnets at our lab. The 45 Tesla hybrid is the world's strongest, and it's also 20 years old. So the technology is a little bit old, but the new magnet is 3 years old, and series connected hybrid, instead of running two different sets of current through it, it's using the same electricity through the superconducting and the hybrid part, I'm sorry, the resistive part of that magnet. So it's wired differently. The path the electricity takes is different, and that's what makes that magnet able to run with so much less electricity, but still reach an incredibly high field.
Excellent. And there was some questions about advantages. Yeah, in a hybrid magnet, you're basically just adding the two together, right? So our 45T hybrid is like a 33.5 Tesla resistive magnet and an 11.5 Tesla superconducting magnet smushed together, married together to make that massive 45T. So that's how they work. And the advantages of using hybrid technology, it's a great question. What do we get out of hybrids that we don't get with just traditional superconductors and resistive magnets? And right now, that answer really seems to be just massive fields, right, Carlos?
The stronger the field, the better the science. That's
Yeah.
what the scientists have always told me. So that's what they're pushing for.
And in fact, in the series connected hybrid, one of the things that's special about that magnet is that it combines high fields, 36 Tesla, and high homogeneity. So it's able to conduct some types of experiments that are really exclusive to chemists and biochemists. And that's part of the advantage of that magnet. I want to say, we have lots and lots of magnets at the MagLab, dozens of magnets at the MagLab. And so each one of them has kind of a special superpower, right? It's not like, well, you could either use the 45T or the 36T, right? There is a reason that those are two separate magnet systems. They have some special superpower that makes it really important to researchers to answer super important questions that help us all have cool new technology or understand diseases or figure out how to protect the environment, all these really important research questions that we're answering, right, Carlos?
Not all magnetic fields are created equal. Exactly. And not all magnetic fields are for everyone. You might think that, oh, I'll take my experiment to the 45T and I'll get better results out of it. But if that's a biological sample, you might be better off on the 21 Tesla 900 megahertz because it is doing something different than the 45 is. So the different magnets have different purposes. It's not always about the strongest field, though. Don't get me wrong, strong fields are good, but the different magnets have different purposes. So if your magnet is right for the 36 Tesla series connected, it might not be right for the 45T. So it just depends what you want to do with the magnetic field. And you mentioned the high homogeneity of it. That's something else that I hadn't mentioned, but not all fields are equal. Some are more evenly distributed than others, and some aren't as evenly distributed. And again, it depends on what you want from your field. So do we have a checklist on our website that says which magnetic field is right for you? That would be a great Facebook quiz.
Yeah, we actually have, for the scientists who come to the lab, we basically do have a which magnetic field is right for you. It's a kind of a match.com for magnets, if you will. We call it a magnet search. And so you look for which field strength or which type of measurement technique you're going to want to do. And we'll spit out a list of the magnets that you can use to do that. There is a question about some of the experiments that we've done using our magnets. I think this is really an important one, right? We don't just build these magnets to have the world records, right? We use them, we share them with researchers around the world who are conducting research to make all these important discoveries. So Carlos, do you want to talk about some of your favorite experiments? I'll see if I can address a few more questions in typing while you answer this one live.
I know that a lot of the experiments, material science is the #1 thing we do. So trying to figure out the superconductors as a material is one of our biggest goals. I'll be completely honest, and I've got what I consider a deep understanding of science, but sometimes I hear the experiments and I'm like, you lost me at what I'm doing is, and then they just get very complicated. What I love to see is how the scientists are working on their experiment. They start getting data. And as the data starts to come in, it's not the data that they were expecting. And I saw this when two scientists locked eyes when they looked at their data and they're like, this isn't matching what we thought. And almost in sync, they started redesigning their experiment to capture what they were seeing coming back from the results. It was a beautiful moment of science, and it happened just completely naturally. I remember one was Dave Graff, and he was looking at the other scientists and said, and they just went right to work. It was effortless. It was an amazing thing to see.
I
I
want to
also, oh, go
I
ahead.
want to clarify one thing that's important about our massively powerful magnetic fields. These magnetic fields are created right in the center of our magnets, right? So the whole MagLab is not magnetic. When our magnets are running, we're not affecting the Earth's magnetic field or anything like that, right? The 45T, for example, the world's strongest magnet, is creating 45 Tesla right in the center of that massive magnet, about a space as large as what Carlos is showing you right now, a little larger than an inch. And that's
32 millimeters.
and that's where the researchers are putting samples of materials that most of us have never heard of. And they're using the power of high magnetic fields to understand the electronic properties of those materials. So one of my favorite materials to talk about is basically a form of carbon that's exfoliated down to a very thin atomic layer. It's called graphene. And in fact, this material has all sorts of really interesting electronic properties that we've been able to understand with much more detail with the power of high magnetic fields. And there's a lot of thoughts right now, when you leave this talk, just Google the word graphene and read all the articles about all the different ways people think that this material might be used to drive future technology, to change technology we have now to make it more energy efficient or more, smaller or more flexible. All sorts of really cool possibilities for this material that, again, most people when I give a tour or when Carlos gives a tour, they've never heard of it. And, this is a material we've been studying for more than a decade. So I think it's a great example of the kinds of research that happens, and just a reminder that these magnetic fields are really being channeled to a very small research experimental space. If we were making massive fields that affected the Earth's magnetic field, we would not be harnessing the power of high magnetic fields for the good of science to make these discoveries.
The parking lot is safe. Your car's going to be there at the end of the day.
Yes.
It is okay to drive by the lab, and it's okay for airplanes to fly over the lab. All things that I've heard people worried about.
Exactly.
I love, Kristen, sometimes we'll get a lab-wide email asking for an exotic material, and I'll be like, wait, gold thread is a real thing and we need it? I saw last year I was in the hall and one of my friends was walking by holding this little container. And I'm like, oh, that's cool. What is that? She's like, oh, it's uranium crystals. I'm like, oh, so matter of factly, she was just carrying uranium crystals to go do her experiment. And I was like, all right, that's a thing. And even yesterday I was practicing a presentation with another scientist. And as he was shrinking windows, I saw in his window, he had his paper that he was working on Neptunian tellurium. And I was like, oh, so now we've got Neptunium at the lab. I mean, these are materials that I thought I would read on the periodic table and never see, but we're working with them. And that's just an amazing thing. We're doing things every day that I'm like, oh my God, that's what we're doing. And it's just remarkable. I love it.
I think beyond the material story, one of the other things that I really want to point out is that 900 megahertz magnet that Carlos showed earlier, the powerful MRI magnet, it's working on things all of us have heard of, right? Trying to understand influenza and tuberculosis and Alzheimer's and Parkinson's and, migraines. And as Carlos mentioned, the structure of COVID-19 and other coronaviruses that we've been studying for many, many years, and that our users who come from all over the world are studying. That's another important point not to forget, right? It's not just the MagLab researchers making these discoveries. It's thousands of scientists from, universities all over the world that are coming here to leverage the power of high magnetic fields. I just want to cover what magnets are made of. This is a question I know we've kind of talked about. Those resistive magnets are made of materials like copper and silver, copper oxides. That's the ones that use a lot of electricity to create strong magnetic fields. Our superconducting materials are made of special superconducting materials. Remember, superconductors only operate at very, very cold temperatures. And superconducting materials are very hard to come by, very rare. And there's actually still a lot about superconductivity that scientists don't understand. So even though we're using superconductors to make magnets, we still have questions. to answer about superconductors.
And I love it when we're using a superconductor to study a superconductor to figure out what the next superconductor is going to be. And that's a real legit thing that's happening a lot, actually. Superconductors also get the best names. We've got IBCO, REBCO, BISCO. And there's materials that we haven't even discovered yet. So those may be the superconductors we've got now. That doesn't mean those are the ones that we're going to be working with in the future.
Exactly. Just one question for you, Carlos. There's a few times it's entered about what we could use to block magnetic fields. And maybe even the series connected hybrid picture is a good example to go back to show that, because the series connected hybrid actually does have quite a remarkable shield on the outside of it so that we can walk down the hall, right, Carlos?
You read my mind. So let's go back to the series connected. Here it is. So the magnet, you can't actually see the magnet because what we've got here are 3 large plates that are blocking the magnetism from going out. So what they are is essentially they're iron slabs that are being magnetized and receiving the magnetic field so it doesn't extend past that. So we can have magnetic fields that are actively shielded. We have some magnetic fields that are passively shielded. And those are 2 different methods of blocking magnetic fields, and we use both of them at the MagLab. But yes, it is possible to block magnetic fields. And I know that sometimes we've got computers that we shield to protect the computers. So that way they're able to be working close to the magnets.
Carlos, do you know how a magnet's strength drops over distance? I know you showed those lines. I don't recall the precise equation that does that, but do you have anything to share about that? I mean, I know that we can stand a certain distance away and that the field does dissipate quite rapidly, because it's really centralized there in the center of that magnet. But do you have anything to share?
I was told there was going to be no math. It's an exponential decrease. It actually drops off very rapidly. So you can be right next to the magnet in a pretty strong field, but as you start walking away from it, it drops off very rapidly. That's why you can be 20 feet away from the hybrid and not in a significant part of its field.
One of our scientists helped save us here. It drops as an inverse of the square. So for those of you who were looking for the answer, and thank you to the scientists who came in to save us in that answer. Carlos, do you have a favorite magnet at the MagLab? It's hard to pick. It's a little like Sophie's Choice. When you work at the MagLab, you kind of love them all. But do you have a secret favorite you want to share with everyone?
I like showing off the hybrid. I want to spend more time around the series connected because I've been told that it quenches very interestingly, and I want to see that. I like the split cell actually, and it might be because it's the only one of its kind in the world.
Yeah, so, there's some favorites all over the lab. It's hard to pick just one. When we think about what all these magnets do and are, there's still a few more questions about how much helium we use to keep our magnets cold. I actually found an article about that yesterday, and it changes all the time, right? Because it depends on how much we're running and what we're doing. But it is quite a bit of helium. And I just want to share, the MagLab actually is really great at recycling our helium. So we recover and purify and reliquefy our helium so that we can reuse it. Helium is not abundant on Earth, everyone. So we try to be good stewards of the helium that we have. Some questions about magnets and whether they can hurt people. I just want to be really clear. First of all, safety. Very important at the MagLab. We all take extensive safety training. People who work in high fields have additional training. Safety is a huge driving force at the MagLab. And so everything that happens, takes all of that into account. But maybe you can talk a little bit about that question and weave in the idea of a quench, one of those keywords that you mentioned there.
Yeah. So, I almost forgot what the question was again. Oh, do magnets harm or hurt people? So no, there's no research that has shown that magnetic fields are harmful to people. That's how when we're in an MRI, we are inside of a strong electromagnet, and the doctors are able to actually use the magnetic field to learn about what's going on inside our body. The great thing is that you get an MRI on Monday, you can get an MRI on Tuesday and Wednesday and Thursday and Friday, and nothing's going to happen to your body, as opposed to an X-ray, where if you get an X-ray done on Monday, you can't get an X-ray for a few days because your body needs to get rid of this radiation. So magnetic fields are perfectly safe. I know that there are some magnetic bracelets that people wear for their health. And I don't want to comment on those other than that magnets do not harm people. So there is no bad coming from the magnetic fields.
And can you just tell everybody what a quench is? I think I answered this actually with a link in the chat, but for those of you just looking to have it explained, it's sort of a sudden loss of magnetic field strength, right, Carlos? That's all it is. It's a fancy name.
A quench is when a superconductor does not superconduct anymore. And it does that because it has gone above the critical temperature that it needs to superconduct at. And what happens is that the wires that are carrying the electricity immediately become resistive. They start to create heat. And the problem is that as they create heat, all the helium around it starts to boil. And that heat needs to go somewhere. So that helium boils off. We've got to take it all out of the magnet rapidly, or else the magnet can harm itself, because liquid helium expands when it becomes a gas, very much so, and the magnet could tear itself apart as that's happening. So when the magnet quenches, and we expect magnets to do that, we have fail-safes built in to protect the magnet, to protect the people, and usually the helium gets vented out of that immediately, very rapidly, but it's also very loud and spectacular. You'll see a big cloud sometimes of liquid helium being expelled. So that's one of the things that we can do.
Here's a question, I think, from one of our participants about if gravity is a huge magnet, how does it work on us if we're not made out of metal? Could you take that one, Carlos?
I have to remind everyone that gravity and magnetism are different forces. They act differently and they're caused differently. Gravity is a great debate going on in the theoretical science world about what gravity is, what causes it, and how it works. I remember somebody wrote a paper not too long ago saying that gravity is not a thing and there's other forces responsible for it. But gravity and magnetism are completely separate ideas. So it's not magnetism that's keeping us on Earth. It is all because of gravity, and that's different from magnetism or electricity for that matter.
And Carlos, there's a question that I would take myself, but I'm going to give it to you, about the idea of how magnets help us learn more about diseases. Could you give people some examples of some of the really cool stuff that are happening in the 900, like Sam Grant's work and Victor's work with sodium MRI, for example?
Yeah. So when you go to a hospital and you get an MRI, they're using a 1 or 2 Tesla magnet to show you what's going on inside your body, and the doctors or the machine makes an image that lets doctors see your body organs, your lungs, your heart, your kidney, your liver, but you see the big picture of what's going on in the body. As the magnetic field gets stronger, we're able to actually visualize more. So on the 900, we're not putting a whole body in there. We can't, but we can put a blood sample in there. And with that blood sample, we can see the proteins and how the proteins are working. The great thing about that is that viruses like COVID-19 are working at the protein level. So we're able to see what the virus is doing, how it's attacking, how it's reproducing. We can find out all the secrets of the virus just by putting it into the magnet and watching it work. And we're able to do that with our magnet and the 21 Tesla 900 megahertz. And I always say the 900 because it's the frequency that's actually more important than the strength of the magnetic field. So that 900 megahertz allows us to really see what those viruses are doing at the protein level. Same with the sodium that Victor Shemko is working on, and what he's doing is as cells are dying, they're actually giving off sodium and potassium. There's an intake and an output, and we're able to actually focus on the sodium level and actually see if the cells are getting healthier or getting sicker almost immediately by focusing on the sodium instead of what a traditional MRI does, where it focuses on the hydrogen. So we can focus in on something different. It's kind of like looking at a different target, and we can get more information almost in real time and see, hey, this treatment is making the patient better or worse, depending on what the sodium levels are.
And Carlos, there's one more question, which I think is just too good to not take before we wrap up, which is, how do magnets help us learn more about planet Earth?
Oh, so, excuse me. I've got friends in geochem. I've always liked geochem. There's the machine in geochem that's one of my favorites, and it's not a magnet, so I didn't use it. But they've got the induced couple plasma mass spectrometer, which is just a fun machine, and it's got a window where you can see plasma in the machine. So what you can do is you can use the magnetic field that is in that machine, and what it does is it takes like a rock sample. I know that a lot of our scientists are working on basalts. So they'll take a basalt, which is a type of rock, volcanic rock. They'll put it inside the machine, the mass spectrometer, and the machine will break it up into small atomic sized pieces and then send them flying through the mass spectrometer, and then the magnetic field is going to redirect them. And because the masses are different, they end up in different areas, and that machine will let us know, hey, this rock is composed of these materials. And basically that's just the very heart of what geology is studying these rocks, finding out where did it come from, what is it made out of, what is it doing. And we can't do that without the magnetic fields to separate out the materials so that we can see what they are. And I've spent too much time in geochem, I think, so.
How about that, everyone? Well, we could obviously stay here all day and talk about magnets and the MagLab, but we have so many other amazing sessions ahead for you throughout the week, throughout the next 2 weeks. Remember, those scientist speed sessions are sort of like ask me anything. So bring all of your questions about magnets and research and what scientists are like to any of those scientist speed sessions scheduled in the next couple of weeks. I hope I see some of you back to do some chemistry cooking with us. And I want to know how many of you will be able to escape the MagLab's escape room. It's an escape. We'll see. So we'll see how that goes later this weekend. That's next weekend, next Saturday, and the week after that. Carlos, thank you so much for this amazing field trip. Thank you to everyone who joined us live to ask all these wonderful questions. And for those of you watching this later, I hope you also have fun, and feel free to email Carlos or myself more questions about the MagLab.
Yeah, feel free to come to the MagLab website. We'll have more information about the summer camps and the formats and the dates for that soon. But one last thing I'd like to say as I sign off to everyone is to remind everyone to be who you are, stay nerdy and stay geeky, and be true to yourself. So from my baby Godzilla and Groot and myself, thanks for joining us.
Thank you, Carlos. Thank you to everyone for coming today. See you at an open house event soon.